Thank you very much. Thank you to the organizers and to everyone who came here. Very nice day. I'm looking forward to the talks and such a nice diverse community. So the title of my talk, Quantum Absorption Refrigerators, case study or a toolbox in quantum thermodynamics. So in the previous talk, we've just heard about NV centers as a toolbox for experiments in quantum thermodynamics. And indeed, the main message of my talk is that quantum, similarly, or from a theoretical point of view, quantum absorption refrigerators were a very fruitful playground for us in theoretical studies along the line of quantum thermodynamics, exploring different aspects of the theory, different applications, different questions. So I'm not here to tell you that quantum absorption refrigerators are the future and it's the best new technology, but really it's a nice playground to test ideas and develop methodologies. So yeah, that's my drawing of a quantum absorption refrigerator. I'm sorry. I'm not in this area. So yeah, very primitive picture. Absorption refrigerators are continuous autonomous machines. So unlike the previous talk, we are not going to have lasers here burning the system. And what we would like to do, I'm going to briefly first explain the system. Okay, so it must. So what do we have? Oops. So what we would like to do, I hope you can see my mouse, is to, the action of a refrigerator is to extract heat from this cold bath, from the blue one, and we have to dump it somewhere, and it's going to be dumped into the red reservoir, which is hot. Now, obviously, we cannot do it in a spontaneous way without additional work. And in this type of machine, the work is in the form of an additional heat bath. So that's the orange entity, which is another heat bath. We refer to it as a work reservoir. So in the direction that we would like the machine to act, we are going to absorb heat from the blue one, dump it into the red reservoir, and this is going to be, the process is assisted by the orange work reservoir. So what about quantum effects? In my abstract, I put many ideas, but I'm going later on to focus on one aspect. We've heard also in the previous talk, coherences between the eigenstates of the system in the steady state limit. That's where quantum effects could be, hopefully, could be used in a fruitful way. So that's one question that one may ask. The second question that I'm going to focus today, and that's where I put this arrow picker, what happens when we go beyond the natural trivial weak coupling limit, but now start to consider the quantum system to be strongly coupled to the environment. This is not necessarily a quantum effect, almost in classical systems, nanoscale, small systems, classical systems could also benefit or not from this strong coupling effect, but I'm going to focus here on the quantum machine. Another topic that we've been working in my group, but I'm not going to have time today to dwell on, is the question of fluctuations. We have heard about it in the previous talk. We are going to absorb from the heat bath, but we also have the fluctuations processes where we instead also see heat coming and going to the system, to the bath. Questions that one could explore, 4 and 5, I'm not going to touch them at all. What happens if the bath are actually not infinite? So maybe it's closed, it's a closed system maybe, pretending to be a bath for some time, and questions about the behavior in short time, so just the steady state and so on. So a little bit about myself before I get into the details. Why do I study quantum thermodynamics? We heard from Sebastian and his path. So very briefly, I'm intrigued, yes, I guess everyone here, by complex systems in the sense of multi-layered system. We have so many aspects here, whether it's a quantum nest, a many body, the fact that these systems are noisy, non-equilibrium. And this is the angle that I'm bringing here. There is a lot to learn from chemistry. I will tell you, there are some chemistry around in the room. That's my background. And I will try to show you where research in theoretical chemistry, at least limited to that area, is very useful in this domain. So what do we do in my group? We are a theoretical / computational group. We are trying to develop techniques for principles of quantum thermal machines. So indeed, it's about principles mostly. We are not into simulating the dips and peaks of a specific system, but more about the guidelines. So for example, I mentioned already the energy conversion devices, the quantum absorption refrigerator as an example of type of system we are interested at. Energy storage system devices, quantum batteries, for example, quantum sensing in the sense of, for example, thermometry, information processing. I will not get to that. Okay, so that's about the different types of actual systems that we have been thinking. And now the question of realizations. So many of our studies are about qubits in a bulb that we heard in the previous talk. You can model it and realize it experimentally in different setups. But also another angle that in my book we have been taking is to think about molecular quantum machines. Maybe that part is not well represented. Yeah, okay, you can see maybe, just need to press hard. So molecular quantum machines, a very rich community, and this is a review article from an experimental group summarizing some of these very neat experiments. So it's a single molecule experiment, and it's quantum in the sense that the transport is actually quantum coherent. And in particular here, you can have these two-part interferometry realizing the system, and it's supposed to realize a thermoelectric energy conversion device. So these are the type of systems we are interested in. Again, a little bit myself. So I'm originally from Israel, if you wonder about my accent, but in the last 15 years, okay, I've been here in Toronto, not too far from here, this took when flying. And we have heard about quantum thermodynamics hub. So Toronto, I would like to suggest is a very good place for quantum thermodynamics. Summers, very magnificent, and we also have nice winters. So it's really up to you. Welcome you to visit us. Okay, so the outline of my talk, I think I will stay with 1 and 2, so no worries. But some references if people want to check some of the other works from my group. Introduction, I'm going to talk a little bit more about quantum absorption refrigerators, QAR for short. And I will also begin with the classical description. So you have also in the previous talk. It's always useful to go back to the classical domain and think what can we offer beyond it. And I will indeed focus mostly on the strong coupling limit. We have had different techniques over the years developed to study quantum dissipative dynamics beyond the decoupling limit, but here I'm going to focus on these 3 publications from the last 2 years. And yeah, we'll get to them. And they are all on the same technique. And let me already tell you, it's about a method called reaction coordinate. You can hear the chemistry in the background. As I've said, I will not have this time, but maybe I will touch a little bit about the issue of quantum coherences. What is the impact of coherences in quantum absorption refrigerators? The answer is depends. Fluctuations, again, I don't think I will get to that, but maybe just the spirit of the questions and the motivation for us to study fluctuations in these machines. Okay, so this machine, now jumping to quantum absorption refrigerator, the title of my talk. This system was actually suggested, or the model that I'm going to focus on was suggested 65 years ago in this nice paper. And over there, it was suggested as an engine. But today I'm going to present it, and many people did a review on it. Many people worked on it as a refrigerator. So here's a model, and let's present it. It's a 3-level system. So these 3 levels at the center are, let's say, note them by, yeah, bottom level 1, 2, and 3. And we also have 3 heat baths, as I've had in my minimal illustration on the first slide. This comes from a graduate student. He's better than me in illustrations. So we have these 3 heat baths, the cold, which we would like to cool. Furthermore, the hot one, where we are going to dump heat, and the work one, which is the one assisting us in this operation. So already in this original study, you can see that there is this concept of a filter. So the design of this machine is such that each bath is coupled in a specific way to the system. So it's a specific design. You may ask, how do we realize it experimentally? But the design itself comes out with this specificity. So as you can see, the cold bath only allows this transition from the ground state to the middle level. The hot bath allows transition from the top to the bottom one, and the warm bath allows transition here in between. Again, that's something that you can think about as being realized using filters. I'm already jumping to one result that I would like to highlight here. What are the types of questions that one could ask? One question, for example, is about the cooling window. We would like the system to operate as a refrigerator, where heat comes from the cold down to the hot. Obviously, it can act in the opposite way as an engine. And the cooling window, one can calculate it, and I will give you a brief proof immediately. And one can show that to actually have the machine operating as a refrigerator, you need this gap. Theta cold is a gap between the ground state and the middle level to be small enough relative to the temperatures around. So one can tune the energy of the energetics of the system and realize the refrigerator. Okay, so continuing with my introduction, this is taken from the reference at the bottom. Many people have worked on these systems, coming up with different designs. If you wondered about the three-level system, one could come up with qubits, realizing this machine. So just as a general context, that there is a big community thinking about different modifications to this model. And experimentally as well, I'm not sure indeed what has been most recently done in the experiments, but at least at the left side is a proposal to realize it using a Josephson junction where it couples these three modes. And one could come up with, again, the design of these parameters, such as you can pull the cold bath. And in the right-hand side, it's an experiment where, I don't know if you can see very well, but there are three spheres over there, and these are supposed to be the three ions. And there are three different, okay, here focusing on the three ions with three different modes. Again, the idea was to extract it from the cold mode and dump it into the hot. So as you can see, these are a highly engineered system, and that's back to my point that I'm not here to sell it as the next most promising technology. Okay, so to the Hamiltonian, we all like to be concrete and actually talk about the Hamiltonian. This is taken from our paper last year where we focused indeed on strong coupling effects. Very simple Hamiltonian, the three-level system, 1, 2, 3. And we're assuming that the bath are collection of harmonic oscillators, so just bosons. And the main game here, as we have said, is these selective transitions. So these are operators of the system that are coupled to the bath. And the idea is that, again, the cold bath C only allows transition 1 to 2. The warm bath 2 to 3, and the hot 1 to 3. So that's just for people who are in this concrete Hamiltonian, I thought to bring it early on, so you have it in front of you. Okay, I will skip this one. So let's begin with a classical discussion. So we have this picture in mind of three-level system, and we would like it to act as a refrigerator. Suppose we are in, what was it, the 90s, where stochastic thermodynamics is only around, we don't know anything about quantum thermodynamics, and we would like just to think about this as a classical stochastic machine. How do we approach it? Well, we would think about the population of the levels, and we would write down as a master equation, continuous time process. We can write down an equation of motion, first order differential equation for the populations. And for example, the first row describes what happens to the ground state population, and there is a rate, there is a rate constant K1, 2 to take you from level 1 to 2 and acted by the cold bath. This one, for example, takes you from 1 to 2 and acted by the cold bath, and this one takes you from 1 to 3 and acted by the hot one, and so on. You can come up really by hand and write down these equations. And similarly, you can write down, again, coming from stochastic thermodynamics, and write down expressions for the currents, for the heat currents between the system and each of the reservoirs. And I'll solve it in the steady state limit. So that's where you would just say, okay, I'm in low time, forget about the initial conditions, let's solve it in steady state. We get the population in steady state, we plug them in the expressions for the heat current. And beautiful, we get the expression for the cooling current. The denominator is a monster, but that's fine. And we can immediately calculate immediately the cooling condition just based on our sun convention. You can check when is the cooling current positive. And the results that I've shown you before about the cooling condition immediately pops up. So we don't need quantum effects here, or we don't need to think deeply about quantum mechanics. It's just a fully classical description gives you the cooling condition. You can click on and look at the coefficient of performance, which is related, complementary to the efficiency. And one can show that it's actually very simple. It's just the ratio of the energy parameters here. So that is again, you can call it efficiency. So the efficiency is a ratio of these gaps. And it can be proved that it's always smaller than or equal to the Carnot efficiency. And you can keep on, and people have indeed enjoyed entertaining themselves with these models. So what is quantum? Because we are here still to think about quantum effects. So let's take a step back, and now we are coming from this picture of the quantum community. And what we do, obviously, we write down the density operators. You would write down the quantum equation, Hamiltonian overall for the system and reservoirs, total density matrix. And this is where I'm just sketching what everyone has been doing around. We'll derive an equation of motion for the system itself, for the reduced density matrix. And the typical approach of the starting point is to use a perturbation theory. So that's a weak coupling limit that I mentioned before that we would like to go beyond. The standard approach is to assume that this interaction is weak, and you derive your expressions to the lowest order in this interaction. And for this model, again, one can follow these steps and you will derive, let's call it Redfield equation. But in fact, here, for this specific model, you will get an equation of motion that looks like this stochastic thermodynamics. So the quantum part here is really just in the rates. And the rate constants are short. Yeah, you dig inside, you will find the Bose-Einstein distribution function, as well as the spectral properties of the bath, which you could engineer and maybe also get some interesting effects. But as we've said, in this model at weak coupling, there is really, you get a question of motion for population. Yeah, so that's for the basic calculations that you do with weak coupling proper systematic derivation approach. It will give you just an equation of motion for population. So this naturally begs the question of what happens beyond the weak coupling limit. And I told you there are a couple of questions that we looked at in the past couple of years, for example, coherence, fluctuations. Today, in 10 minutes or so, I will talk about what happens beyond the weak coupling limit. And I'm really here on a mission, because what happens is that if you use a weak coupling limit and go to your experimental friend and come up and provide them with your predictions, it is an important question to ask whether these predictions are valid beyond the very extreme weak coupling limit. What happens once, eventually in the experiment, the interaction is finite? What should the experimentalists see? So it is, for us, a principled idea to go beyond the weak coupling limit, not just as another calculation, but as a way to understand, to come up with predictions that are hopefully relevant for reality. Okay, so what do we do when we want to go beyond the coupling limit? One way is to look back, and my background is chemistry, and that's what one can do here. And indeed, again, part of my discussion here is to let you know that in chemistry, people have looked for many years and at systems going beyond the weak coupling limit, and that's because they think about reactions, and reactions happen beyond the gas phase reactions. You have reactions in solution. And the very basic reaction is just electron transfer, where you have, okay, this charge, the minus sitting on A, and then you would like the charge to go to B. And one of the most beautiful theories here was developed, and there were many people contributing, but one of the celebrated results came from Rudolf Marcus with Nobel Prize years ago. And the appreciation, the understanding was exactly that the solvent is playing a crucial role in this process. So my solvent here, my drawing now based on PowerPoint a little bit better. So these are the solvent molecules, which are polar. And the idea is that the blue side, here at least, is positive. So it's, as you can see, shielding the negative charge sitting on the A. But what happens here is that as you go from the top one to the bottom, there are some fluctuations in the solvent, and they can facilitate the transport of charge from A to B. So the solvent is really the central player here. It allows the transfer of electrons from A to B. Okay, so moving on. So that's the basic. We see that theoretical chemistry indeed relies significantly on strong coupling effects. And yeah, so let me indeed now move on to the actual flavor of strong coupling technique that we have been using. It's not just us, there are a couple of groups in Europe, especially adopting this technique. And I think that this is one of the first papers that started this approach, again, in the context of electron transfer reaction in biomolecules. So the principle is quite simple. Yeah, it's not very complicated, but here maybe in the language that is more clear to us, there is a qubit, this two-level system, and this represents in the specific context electronic states. And this is a reaction that, again, we would like to mimic of electron going between these two states of this qubit or reactant and product. And in this picture that they came up here in this theory paper, the idea was that Y is the degree of freedom of the environment. And out of the many degrees of freedom of the environment, there is one, again, this Y, which is strongly coupled to the system. And this Y, if you can see here, is furthermore coupled to many other degrees of freedom. So they came up with this hierarchy of interactions where, again, the system itself is coupled in particular to 1 degree of freedom, which we are going to refer to as the reaction coordinate, because that's the one leading the process. And this one is coupled to, let's call it a secondary bath, which is of course important for the dissipative process. So that's an approach that has been around again for about 30 years in the context of chemical reaction. But a couple of years ago, it started to enter the quantum thermodynamics community. And let me indeed present it in taken from this book. Yeah, it's a book, present the method. And that's a technique that we have been using. And I will, as time allows, I will tell you a little bit about our results. So the method is quite elegant and again, very intuitive and simple. The idea is that we have this system, the purplish ball, and it is coupled to a bath. Let's say, assume now that again that there are bosons, and there is a certain spectral density function that describes the coupling. So that's a Hamiltonian, HS, bath, and the coupling, and again the function that describes the environment and how the system couples to it. And the idea is quite simple. One can come up with normal mode transformations since the bath is harmonic. So there is a way to manipulate these modes and come up with a new Hamiltonian such that simply we take 1 degree of freedom from the bath and now think about it as part of our system. But one, of course, should do it in a smart way such that the residual coupling of this extended system to the bath is weak. And that would be the hope of this transformation. We enlarge the dimensionality of our system. So now we have an additional mode of frequency omega, it's harmonic. And it is coupled to the system with strength lambda here. And there is a different now bath. It's still harmonic, but in principle, you took 1 degree of freedom and you rotated it. And still you can describe everything in terms of the spectral density function, but obviously it's different. So this coupling of the extended system to the bath is, you have to work it out. So yeah, again, without you don't need to read all the equations, the main point is that from the original Hamiltonian, we know about this environment, its modes, how they are coupled to the system. And based on this function, we can derive for the extended system the new properties, the new frequency that now we are adding to it, and the new coupling parameter. So the main idea of this technique is that if you have strong coupling to the environment, why don't you just redefine the boundary? So the system just enlarge it, find out, redefine the bath such that you can identify an effective, let's call it reaction coordinate, an effective degree of freedom. It's all harmonic here, so it's this transformation is not too bad. And I'll just extend the system, and hopefully this residual coupling is weak, such that now you can take your favorite recoupling technique and run it on the extended system. So this technique, again, has been used in the past for quantum dynamics. And about 2-3 years ago, when Nick, here, the left side, when Nick came to my group, indeed, I suggested to him, why not we try to apply this reaction coordinate technique to problems in quantum thermodynamics. So there's not many or a few studies thinking about the operation of machines using this technique. And in particular, I put in the second point, one can operate this technique in a numerical way, just punch the machine, have an extended system. But we've hoped, and that's indeed your results. We hope to use it actually as a way to gain some fundamental understanding, analytical understanding of the system. So back to the question of strong coupling. Is strong coupling helpful for the operation of your machine? I told you about the cooling window, for example. Then we actually come up with something more concrete about the role of the strong coupling in the cooling performance, in the efficiency, in the cooling current, and so on. So Felix at the right side was also involved, and I think I saw that he's online. So again, yeah, these are the three publications most relevant for the study, and the one at the bottom is the one I'm going to focus on now in the last 5 minutes. Yeah, also. Yeah. So I told you about this idea of reaction coordinate. Again, this is one of the ways to incorporate strong coupling techniques. There are many others. Today I'm focusing on this one. So moving from A to B, this is what I've described so far. You have a system coupled to a valve, strong coupling. Let's identify this mode that is very important to us and add it to the system. So that's A to B. What we did in this recent study, it was recently accepted to PISMA-S, is to go furthermore and get to D. And I will not have much time to describe it, but we did this process exactly because we wanted to be able to do some analytical work, such that we can derive expressions for this cooling window and think about what it means to get some coupling. So what happens as you go from B to C is, again, without too many details, is another transformation, which is exact. So going from A to B is exact, B to C is exact. But then going to D, we did a certain truncation, which I would be happy to discuss later on if people are interested in the technical details. So overall, it's not an exact technique, but it should be reasonably or hopefully okay when the cutoff frequency of the back is high. So yeah, so these are the technical details, and I will leave them to later if people are interested. This technique, I would like to emphasize, it wasn't just developed for the absorption refrigerator. Precisely, the idea was that it's a tool that is useful for other problems in quantum thermodynamics. In A, for example, it's really just about the quantum thermalization problem. If you ask yourself, what is the state of the system when it's strong coupling to the back? Am I going to get the canonical state or not? So that was the question that in panel A we explored. In panel D, for example, you can use this technique and look at electron-phonon coupling effects. So this was about a thermoelectric power generator when electron transport is coupled to phonons. And this coupling could be strong. And again, the question was about the impact of strong coupling to the performance. In E, for example, it's 2 qubits, but one can actually think about a one-dimensional chain or lattice and ask questions about the phases of dissipative spin chains. And finally, okay, it's in C. So C is indeed the model that I'm focusing on today. So this is Hamiltonian again. That's what I said at the beginning. I wanted to show quickly the Hamiltonian, so we have it all in front. So that's the starting point, and I also wrote this J of omega, which will refer to, as I mentioned it a couple of times, the spectral density function of the bath. It's a weighted density of states. So it's not just the density of states of the bath, but also it describes the coupling strength. So the main parameter to take from here is this lambda in the spectral density function, which describes in our picture, the coupling parameter between the system and the bath. So I'm going to show you results as a function of this lambda. When lambda is small, that would be our decoupling limit. As we increase lambda, the natural question would be what happens. Okay, so let's begin. I described to you the decoupling approach right at the beginning with the stochastic thermodynamics, and that was the cooling window. Epsilon1 is the ground state, epsilon2 is the middle level, and epsilon3 is the top one. So what I'm showing here is a color map to the cooling current. So we would like it to be colorful. That means that we are extracting heat from the cold bath. And there are 2 axes. So I'm showing it results as a function of the coupling strength, lambda, and as a function of the splitting rule. So when the splitting is small, that's when the system cools. Yeah, so when the delta is small, that's beneficial for cooling. You can imagine intuitively, you need a small gap to allow using the cold bath to make this transition. So the white region describes no cooling. So first, yeah, small delta is when you can cool, and furthermore, the prediction of the recoupling technique, as you can see from the color scheme, is that as you increase coupling, and of course, I just push the method beyond where it's valid, you get more and more, you extract more and more heat. So that's where indeed you should wonder, I'm giving you here a prediction, couples more and more strongly, and you should get, the system should extract more and more heat, and is it a valid prediction? It's all based on a weak coupling technique. So this is now the Hamiltonian after doing our effective Hamiltonian transformation. And you remember I had this A, B, C, D, where A to B was a reaction coordinate transformation. But as I've mentioned, we continued to 2 other steps. And these 2 other steps allow us to derive what we call an effective Hamiltonian. And this technique is applicable to other problems. So I really want to advocate it as hopefully a nice tool for quantum thermodynamics. And one of the nice aspects of it is that what we find is that you can identify the system's Hamiltonian only that its energy parameters are different. So instead of the original delta, which was a splitting between the ground state and the middle level, now there is, okay, I'm going into the all details, it's changing, and exactly the parameter that controls it is the system back coupling. So lambda, as you can see, which was the original system back coupling, decorates here many of the expressions. So with this effective Hamiltonian, everything is now messed up, but still, it's not, we can use it for analytical work, but the coupling parameter, which was originally just dictating the coupling strength between the system and the back, now appears in many ways, but in a fundamentally simple way as renormalizing parameters. So it's, we can still make sense of it. So here's a result using our strong coupling technique based on this reaction coordinated approach. Again, the axes are the delta is a splitting, and the other axis is lambda. And when it's colorful, it means you are able to cool. And as it gets reddish, it means a larger cooling current. So the main observation is that you see this tilting of the cooling window, which is not very surprising. Initially, we got it numerically without a deep understanding, but once we had this analytical approach, it was actually very clear. What happens here is that the original energetics and original energy levels of the system in our approach are being modified. So in fact, it's the same cooling window, it's the same cooling expression, only that the energy levels are not the same as they were originally. That's one interpretation for the strong coupling limit. The system's energies have to be dressed by the system back coupling such that the cooling window changes. Okay, so back to the big question, is strong coupling useful or not? So as you can see, it's a mixed answer. If you want to have cooling in a regime that you didn't have before, yes, previously in the weak coupling limit, we couldn't cool here, but now there is a way to cool in this parameter regime. On the other hand, where we had cooling before, now we do not have it. So it's not a fully positive or negative result. You can see there is a modification to the cooling window, but overall the cooling current is smaller. So this positive significant result that we've had before, this getting to very strong cooling performance, is of course is not valid once you go to and use a proper technique. And I will skip this one. Furthermore, you can ask, what about the efficiency of your machine? So that's what I'm showing in the x-axis, the coefficient of performance, which is a ratio of the cooling current to what you have to invest, what we call the work current, and in the y-axis, it's the cooling current. So if you just focus for a moment on the full lines, and they're going from the blue to the, which one is the next one, to the reddish and then to the grayish, that's when we increase the coupling strength. You can see that the maximum efficiency is being reduced. So the maximum efficiency here, and you can reach up to 0.5. And as you go to stronger and stronger coupling, you realize that you cannot reach that efficiency. And furthermore, when you compare to the weak coupling limit, that's what we mentioned before, and you check the magnitude of the cooling current, it's not as good as you had before. It's reduced. So overall, you can conclude that here there is a detrimental effect of strong coupling. I'm not going to claim that this is a general result. It really depends on the model. But overall, once you go to strong coupling, I would say your intuition that's when it's hard to just use a plain intuition that we have, because you get so many additional effects. You get cooperative effects, you get effects beyond low order. So typically, it's just hard to come up with a design that makes use in a positive way of all these effects. Okay, so the take-home message indeed for the strong coupling effects in thermodynamics should be, again, talking to our experimental collaborators, should we advocate for it or not? Should we suggest to them, move for it or not? So here is my advice. So I just took it from the old books. Maybe not do good, sick peace and pursue it. So let's see. I mean, it's useful in general, but also for us. So the first part is, don't abuse the recoupling limit, because the predictions are not going to be valid. The second part is, the audition, I would suggest develop and apply these tools. So that's the right way to proceed. And the last part is about peace, and obviously peace requires compromises. So that's indeed, you should accept, to get the best efficiency and the best power output. So coupling tells you that there are compromises to be made. You can get coherences to play a role, maybe in the recoupling limit they're not doing much, but there could be other detrimental effects. So I guess I need to conclude. Okay, so I will jump to the conclusion page. I did want to say a few more words about fluctuations, but I knew that I won't have much time. Okay, so indeed, in summary, the quantum absorption refrigerators are a good test bed and playground for us to develop technique, and I presented to you one approach that we have been using in the last 2-3 years. And I would like to, again, give this double arrow between quantum dynamics, quantum dissipative dynamics, and quantum thermal machines. Hopefully now with these techniques, we can go back to quantum dynamics. I didn't get to talk about coherences, but maybe that's where I could mention that obviously there are destructive and constructive interference effects, and oftentimes people just celebrate the constructive effects. And that's about, again, realism, where models can show also the destructive effects. And with that, I would like to indeed acknowledge and thank the students who worked on this project. That the parts that they described was led by Nick. Some of you met him in the APS last week. And Felix, he was an undergraduate group and student in my group, and he moved to Berkeley. And I also wanted to mention that in Toronto, we also have a center for quantum information and quantum control. And I don't know how much you can see, but we have activity again encompassing from chemistry to physics, computer science and engineering, and I really welcome you to visit us. Thank you very much.